We're going to continue with our paper 2 discussion of our practice exam for April of exams. So, question number 3 is a question about ideal gases and pressure and volume. A few things. So we have a graph interpretation. We have an outline, which is pretty straightforward. Should be able to find that pretty easily. Then we need to use the graph to show that it's taking place at a constant temperature. And then finally, we need to find that constant temperature here in letter C. Okay, so let's start with the graph and talk about it just for a second. So I have a nice linear graph. My units are 1 over volume and pressure. I've got 10 to the 5th pascals, and I'm in cubic meters. So, like I said, you can look up A pretty easily, the components of an ideal gas law. Let's focus on B. I want to show that it's taking place at a constant temperature. So in order to do that, I want to be able to say, I want to use my ideal gas law, PV equals nRT, and I want to show that this T is constant. So in order to do that, I'm going to simply rearrange it for T, and I'm going to say that T equals PV over nR. And if I can show that all of these are constant, then I can show that T is constant. Well, I know that N, being the number of moles, is constant. R, by its very name, is the ideal gas constant. So that's going to be constant. So my denominator is going to be constant. But what about my numerator, PV? Is that going to be constant? I can find that from the graph. If I have 1 over V and P, then the slope of that line, which we know is constant, the slope is going to be the change in P over the change in 1 over V. If I now rearrange that equation, or get rid of the fraction here on the bottom, I would come up with PV. I'd invert and multiply, coming up with PV. So, therefore, PV from this graph, being the slope, is constant. So I can say that T is PV, shown by the graph, is constant. And in R, because we have the constant amount of moles and an ideal gas constant is constant, so therefore my temperature is constant. Next, it wants us to calculate that temperature. If it is constant, then let's calculate that temperature and make sure that we report it in degrees Celsius down here at the end. So, I start out with some information that the molar mass of oxygen is 0.016 kilograms per mole. I know that my mass is 0.05 kilograms, and I need to know moles. So if I have 0.05 kilograms, then I'm going to take that times, say I want to get rid of kilograms, so that's going to go on the bottom here, put the mole on top. Now when I multiply that out, the 2 kilograms cancel, leaving me with just moles, and I come up with 3.125 moles of O2. Ideal gas constant is going to be 8.31. And we're using that same equation, T equals PV over nR, in order to find it. So I'm just simply finding the different variables. If I have 3.125 times 8.31. But now I need to find this PV. So I'm going to go back to my graph. And when I go back to my graph, I'm going to pick 2 points that take up as much of the graph as possible, but are also definitive points. So I'm going to choose 8 and 0.6, and I'm also going to choose this point all the way up here. So it's going to be 1 times 10 to the 5th pascals, and over here it's going to be 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's, each one is 0.2, so this is going to be 13.4 as our value. So our increase, our rise, is going to be 0.4 times 10 to the 5th, and our run is going to be 13.4. So I'm just simply going to have to find the slope of that. I would take 0.4 times 10 to the 5th divided by 5.4, and I believe you come up with 7,407. Going back to my problem, I can say that my PV is 7,407. We'll worry about the units later. But now I have all of my information. So this is 7407. Doing the math, making sure that I put brackets around or parentheses around everything, I come up with a temperature of 285 Kelvin. Doing some conversion, I need to go from Kelvin to Celsius. So I know that it's minus 273. So I'm going to take Kelvin minus 273, and I get approximately 12 degrees. 12 degrees Celsius. Okay. Question 4 talks about the visibility of clothing, and it's going to look like some refraction that we're talking about here. So it gives us a little background, a little context. Monochromatic light, not all that important in this particular case unless we want to talk about rainbows. So we have our light coming in from the normal, measured from the normal at 36 degrees. Angle of refraction is going to be 18 degrees. So the first thing it asks is to calculate the index of refraction of the glass. So I'm going to use Snell's law. In 1 sine theta 1 equals in 2 sine theta 2. In 1, because its error is going to be 1.0, sine of 36 degrees equals, we don't know what in 2 is, times the sine of 18 degrees. And so rearranging that, it's going to be the sine of 36 over the sine of 18 is in 2. Be careful not to just say it's 2, because it is a sine relationship. So using our calculators and making sure that they're in degrees, we would have in 2 equals 1.9 as our index of refraction. No units on that because it's a ratio. Next question, calculate the critical angle for this light in the glass. So when we're within the glass, what is the critical angle so that it doesn't bounce back out? So we're looking at some critical angles here from within the glass. So we want to be able to say what's going to happen when in 1, which is now the glass, and in 2, which is the air, what happens when those kind of switch places. So in 1 is going to be this second sine is going to be 90 degrees. And we know that sine of 90, the sine of 90 is 1. So therefore, if we have the sine of theta is going to be in 2 over in 1. In 1 in this case being the glass, right? So in 1 in this case being our 1.9. So if sine theta is 1 over 1.9, I'm going to use inverse sine of 1 over 1.9, and I come up with 31 equals theta equals 31.71 degrees is our theta critical. Okay. The last question on this part is light is reflected at point P. Complete the diagram below to show the path of the light as it passes through the sphere and emerges into the air. So, using a quality straight edge, I'm going to simply continue this path of the light. And now I want to start thinking about its normal line. So if I go to a tangent here, so the tangent, so the normal is going to be something like that, where if this is 18 and this is 18, then that is also going to be 18. And we want to know if this is 18 degrees, what is my angle of refraction on the outside? Well, it's just going to be opposite of this, right? So if this is 18 degrees, then my angle of refraction is going to be 36 degrees. And because it's 36 degrees, we can see that this ray and this ray are now parallel. So when I'm driving in my car, and I have my headlights on, and this person is standing here with their vest on, and here's my eye, my light hits off the vest and reflects basically parallel back into my eye, and I can see them quite brilliantly then. Okay, thank you.